Thank you, everyone. Good morning. Today we were talking about problems and solution for seismic protection of a very large prefabricated industrial building in Italy. I would like to introduce what and where. We are talking about a building made in an area that is Lucca in Tuscany. And we were working in the area of DS.Smith company that has already other factories, other areas, and we worked in a brownfield situation. And this is the building that we are going to talk about today. Just to introduce why we are talking about this, we are a precast company, and we have four business areas, and in the ages we moved from just to be a contractor and an industrial company to have a huge engineering part of design. And for example, we explored also the area of BMS and also seismic BMS, and we usually put inside our buildings some sensors, and we invented the Manini Connect, that is a seismic BMS connection between our company and the buildings that we build, just to have a continuous monitoring of the seismic situation of the building, also helped with also the AI, and we are working a lot about this. We are in Assisi, that is mostly famous for the headquarters of Manini Prefabbricati, but also for San Francis of Assisi, that maybe someone you know. We were working with DS.Smith, that is an international company of that makes paper. And you can see the picture there. That is the paper mill that is similar to the paper mill that they are building in Lucca, and all the buildings of this kind of production are made in steel. And this is the particular thing that we are talking about today, because we find out the way to build this building in concrete instead of steel. And this is the first situation for DS.Smith and also for Smartfit Kappa, for all the other important players in this industry. There were a lot of problems to solve. In that area, there is a huge, high seismic area. One of the reasons that these buildings are made in steel, because we saw before in the international lunch with Professor Menegotto, he showed us some pipes and pipe racks. These kind of buildings are quite similar to pipe racks, because there are a lot of pipes inside this building, and so there is a huge interaction and connection with the MEP equipment. And they have severe operating condition for both for durability, vibration, and also, I forgot to write down, fireproofing. There was a huge problem of fireproofing. And the lack of continuity between beam and column joints had some other problems to solve, so a greater lateral deformability, and also the development of dissipative mechanism only at the base of the column. And so we try to solve these problems and to work with the DS.Smith, starting this design in concrete. Firstly, with the BIM possibility to work in a shared environment with all the MEP engineers, because this has been a very important point, because all the pipes had to have a connection with the structure. And so that's the reason why they usually make these buildings with steel, because you can have welding everywhere and whatever you want. And instead, we had to have a very huge design to put embedded plates inside the concrete elements. We inserted the bracing systems. We used a lot of plates to support equipment with a good shape, and the situation has been very good, and the MIP engineer were very happy about the end of the work. And then we had insert also a specific dispositive that are like crescent moon connection between beam and columns. I know that in US you are talking about a lot of talking about functional recovery, and I think there is a committee in ACI that is talking about this. And this building has been designed after also after a huge earthquake. There is no necessity of functional recovery. And we used these crescent moon elements to make dissipative also extra power to the building, we can say. And this is the dimension of the building. We are talking about a building quite long, more than 200 meters in 4 blocks, separated by seismic joints, and with 42 meters. And one of the other complex things where there was an overhead crane that works almost every day with 170 tons of load. And in the seismic area and in that higher level of position, this is a quite complex situation. This is an overview of the building. This is an axonometric view, and just to let you understand what is the complexity, we had, as I said before, significant interaction between the systems and the structural elements. And here you can see some equipments inside, and maybe here we can understand better how was huge and complex the design, because this is Trimble Connect, that is the system that we used in Revit, where we were talking with MEP engineers and always changing every detail. You can see here something that maybe is not usual in US, because in US you have roof also with truss, double slope truss on the roof. Instead, here in Italy and in this situation, we use the V-shape beam in concrete, also because there was a very huge attention to the fireproofing also of the roof, of the structural part of the roof. And then you can see that these are all the pipes and all the complexity that we solved, and you can see somewhere the embedded plates that are on the columns. and on the beams, on the double T roof, in every element, there was the correct and good position of the embedded plates. And this has been a huge challenge, but at the end, making the billet at the end, one of the important things that led us to take this contract was that at the end it was a solution that saved costs compared to a complete steel structure, and also for the life. All the life costs of a building made in concrete compared to that kind of building made in steel, because there was a very aggressive area, very aggressive area. So I finished. There is now the structural engineer that is talking about the technical things. Mark.
Thank you, Manuel, and good afternoon. So let's talk some words about structural configuration and structural performance. One of the challenges of this building consists of the high operating loads that were required by the customer. You can see that we have high values of service loads from 25, 20, 13, 40 kilonewton per square meter. So the loads are very high. Also, in the table I reported the combination coefficient to be used in Italy, and we can see that for this kind of building we have also high values of the combination, the partial coefficient, the partial safety coefficient, that are the combination coefficient. So also the combined load are very high. And there is also the need to maintain operation following the large events we can expect. And the other challenge consists of the limitation on the movement, on the displacement, the deformation. There are limits on horizontal movement. There is a need for a vibration management. There is a need to maintain operation, as I said, following large events. In the table, we can see the very severe limit for the horizontal displacement as a ratio of the interstory height. And also there are limitations on the horizontal displacement of the beams, especially for the beams that host the moving crane. Considering these needs for to limit the deformation, there is a need to stiffen the structure, the precast structure that usually is not so stiff. So it was considered an ordinary longitudinal stiffening made of conventional steel pressing, but with configuration that are compatible with the pipelines that the building hosts. This in longitudinal direction. In transverse direction, there is no possibility to insert bracing. So they were used these special devices shaped as crescent moon or sickle, that are inserted at the joint between beam and columns. So we obtain a partial transfer of bending moment at this joint between beam and column, and this allows to reduce the forces in columns, so we can limit the size of the columns. These crescent devices actually have a nonlinear behavior. We can see a test carried out at the Politecnico of Milan, and on the right we can see the diagram force displacement of these devices. But so they have a elastic plastic behavior, allowing for energy dissipation, hysteretic energy dissipation. But actually, in this design, this project, we used these devices only in their elastic range, limiting the deformation and the force to the elastic limit. On the right, we can see the mechanism allowing for the transfer of movement, of bending moment at the end of the beams to the columns. Here we can see the little springs represent the insertion of the elements within the structure in the transverse direction. Not all the joints are equipped with these devices, only when necessary. We have this is one of the 4 blocks of the paper mill. This is the block A. It consists of 65 columns, and are inserted 163 devices. Take into account that at each joint typically are present 2 devices at the 2 edges, and also the devices are listed at the various level. You can see that there are different lever arm for different joint, because we can tune the optimum movement, the optimum value of bending moment that we want to transfer from beam to column. The modeling and analysis was based on the construction stage method. Following the construction stage, the first stage consists of the construction of the traditional prefabricated structure with pinned connection among precast elements carrying the dead loads. Then there is a stage in which are inserted the connecting elements, that is the crescent devices and braces, and following the application of the remaining dead loads, the application of service loads, the seismic analysis that was carried out using the retrospectrum modal analysis method, and finally the safety checks, strength, deformation, stability, and so on. A few words about the seismic input. The structure was considered non-dissipative, so without damage under earthquake, with a behavior factor 1.5, not given by ductility but given by overstrength. The peak ground acceleration at the site was 0.192 g. The soil was soft soil, category C according to Eurocode and Italian code. Nominal life 50 years, so corresponding to a reference life, a design reference life of 50 years. We can see on the right the fundamental modes in the two directions. Upper right, we have the mode shape in transverse direction. We have a period, sufficiently high period, 2.2 seconds, but is enough to contain the formation that we want. And in longitudinal direction, we have a short period due to the presence of bracing. We also make some simulation to evaluate the performance extension of the building in assuming also the nonlinear behavior. We also showed that the crescent have a nonlinear behavior, and we simulated the test results, the black line, with a model, an elastic, perfectly plastic model, the red line in the figure, assigned to the element in the model. Then we make seismic analysis. The first analysis was carried out at the demand life safety limit, and in the upper right diagram we can see the response of one typical device, the moment rotation response that is fully elastic because we designed it at the elastic limit, and the lower diagram is the base shear versus top displacement under dynamic analysis, but you can see that the backbone curve is practically elastic. And then we make also evaluation at the life safety capacity that is higher than the life safety demand. At this level, we have a elastoplastic behavior of the crescent, and also the global behavior of the building. The lower diagram show a backbone that is diciamo elastic plastic. From nonlinear static analysis, we also evaluated the extra capacity, the overcapacity of the building. Here you can see the ordinary pushover curve, simplified in the red elastoplastic curve. On this diagram, you can see the life safety limit, that is the blue line, and the capacity life safety limit, that is still in the elastic range. This is the difference between the two limits, correspond to that factor 1.5 that represent the overstrength of the building. But you can see on the right of the green line that the structure has more and more capacity. In this last diagram, we represented the curves of the movement at the joint, at all the joints equipped with the device, versus the top displacement of the structure. So we can see the blue line is, as usual, the demand life safety limit. The green is the device elastic limit, so this is the overstrength. But we can also go over, and we can reach this level of the red line, that is the column elastic limit. That is, at this level, we have more capacity, but the column, the concrete column, are still elastic, are within the damage limit. And finally, we have the ultimate life safety capacity when also the columns are yield, the base section of the column yield, and we have an overstrength, a global overstrength of the building that is about 2.5. So before looking at a short video of 2 minutes, I resume these concluding remarks. Lateral displacement in prefabricated buildings can be effectively controlled using a bracing system. However, in some cases, as in this case, these systems may interfere with the structural design and the MEP layout. As an alternative to bracing, especially when the bracing is incompatible with the building design, we can use this particular joint connection that allow for controlling the forces exchanged between beams and columns, controlling the horizontal displacement, reducing the column cross-section, constructing structure with a low probability of damage, even under severe seismic events, thanks to their overcapacity. This strategy allowed the construction of this building as talked by Manuel. Now we can see this short video that resume the things we have exposed in this presentation.
The project by D.S. Smith, an international paper company in Tuscany, Italy, originated from the corporate need to expand its production facility in Lucca, with the installation of one of the largest paper machines in Europe, capable of producing rolls of paper with a width of 7.8 meters at a speed of 1,500 meters per minute. The challenge appeared daunting from the outset, involving the resolution of issues such as the design of a 16,000 meters squared and 26-meter high structure intended to accommodate an unusual density of machinery and equipment. The structure was to be built in a seismic zone, requiring high control of deformations and the ability to handle vibrations from machinery while ensuring the durability of the structures in an aggressive environment. The problems related to drift control were overcome using 2 different strategies according to the needs of the installations. In one direction, special connection elements in the beam column nodes that achieve total or partial transfer of moments were adopted. In the other direction, deformability was mitigated by the incorporation of bracing systems. The adoption of innovative concrete construction systems made it possible to meet the project requirements, minimizing column sections, significantly reducing the carbon footprint, maintaining high durability, and minimizing on-site labor during the assembly of the structures.
Thank you.